Chapter 1 was points, lines, and planes. We talked about the relationships between linear pairs, vertical angles, but it all started with lines and planes. If you recall, a line is determined by 2 points. They're going to be collinear. So my example would be a point here, and then a connection of the points. If the points were A and B, then we name this line AB, and we used the symbol for a line, which is a straight line with 2 arrows going in each direction. Planes are determined by 3 non-collinear points. So if I have 1, 2, 3 points, we'll say A, B, and C that are non-collinear, I can draw a plane around those points. If I were to name that plane, I would just call it plane A, B, C. We had array. Array has one endpoint and extends in one direction. So let's say this is a point A again, and we extend it in one direction. And there's another point here, we'll call it B. A is the endpoint going towards the direction of B. So when we name an array, we use the symbol for array, where the endpoint goes first and the direction of the ray goes second. A segment is made up of 2 endpoints. We use a lot about segments in the upcoming chapters. The 2 endpoints stop there. They're connected by a straight segment, but there is no arrow on the side because this is where the segment stops. If this is segment AB, we can actually measure it. You can't measure a ray because it goes on infinitely in one direction. A segment stops at the endpoints. It has measurable length. So if I had another segment exactly the same as this one, let's say the same exact length, we'll call it CD, I would mark that they were the same exact length by calling them congruent, and I would mark them with hash marks. So as soon as you see this hash mark here, it shows you that AB is congruent to CD. And if I were to name this line segment, I would say CD with a segment bar on top of it, or AB for this one with a segment bar on top of it. When you have a segment that's made up of other segments, there's your example here, you have EF is one segment, you have FG is another segment, and then you have the whole segment EG. Well, the segment addition postulate, remember, says the part of the segment EF plus the part of the segment FG makes up the whole segment EG. So, for example, I'll put numbers in there to make it a little simpler. If this is 5 and this is 6, then clearly EF, which is 5, plus FG, which is 6, makes up the whole length of the segment, 11. So this is 11. We also talked about a coordinate plane. In a coordinate plane, this is a coordinate plane. You have your X and Y coordinates on a coordinate plane. Midpoint is a point that bisects a segment. So let's say we have a segment on a coordinate plane. Call that AB. And I was looking for the midpoint. We know it's somewhere over here. Well, the midpoint is the average of our X values and the average of our Y values. So for example, let's just say that here's my Y values, 0 and 10. Well, we know just by, common sense that the middle of between 0 and 10 is 5. Well, how did we get there? The midpoint formula of our Y values, and I'm saying Y values because this is vertical, which is the Y axis. The midpoint of our Y values would be 0 plus 10 divided by 2. It's the average of our Y values. 0 plus 10 divided by 2, which is 10 divided by 2, which is half of 10, which is 5. And then let's come down here. Well, if we were looking for our midpoint of our X values, and I say X values because this is the X axis because it's the horizontal axis. If I were looking for the midpoint of my X values, I would take 8 and 12 and divide that by 2. So I would do 20 divided by 2, which once again is 10. And if it's the midpoint, it has to be the same distance from each number. So 8, 9, 10, 12, 11, 10. So they're each 1 away, or 1, 2 away from the midpoint. So that's how we know it's in the middle. Well, when you come here with an x and y coordinate plane, to find the midpoint of your x and y values, you combine the formulas we just did up here. You take the midpoint of your x values, or the average of your x values, divided by 2, and then you take the average of your y values and divide it by 2. The distance formula is when you take the square root of your x values subtracted and then squared, plus your y values subtracted and then squared. Alright, then we went into angles. Angles are formed by two rays meeting at their endpoints. So let's say I had these two rays right here. We can clearly see their endpoints. If they share the same endpoint, then they form an angle. When you measure an angle, you're basically measuring the distance between these two rays, or how far apart are these two rays. And we measure distance between two rays using a protractor. If an angle is acute, it's less than 90 degrees. So this example up here would be acute. And we can recognize it's 90 degrees, or it's less than 90 degrees, because when you have 90 degrees, you're looking at perpendicular right here and here. Or you can even look at the corner of your paper. That's perpendicular. Obtuse is when you have, let's bring this down here. It's when you have an angle whose opening is greater than 90 degrees. Once again, as your reference point, here's roughly 90 degrees, and since my angle went past that, then I'm looking at an angle greater than 90 degrees. And then you have your right angle, and that's an angle that is exactly 90 degrees. And we know something's 90 degrees when you see that box there. It tells us that that's exactly 90 degrees. An angle bisector takes an angle and divides it in half. So let's say we have this angle here. We'll say it's 90 degrees. And I give you an angle bisector. Now, I can't just assume that's an angle bisector because I haven't shown the markings that show you it's an angle bisector. Arcs, showing that there are now two congruent angles to each other, show you that this angle has been bisected into two equal pieces. Well, 90 divided by 2 gives you each of these being 45 degrees. Adjacent angles. Adjacent angles means angles that share a common ray. So let's take this angle. And right now it's just one angle, but let's add another angle to it, say here. And as you can see that both angles share one common ray. That makes them adjacent. If I were to take this ray away, then you only have one angle. So you no longer have adjacent angles. So adjacent angles are two angles that share one ray in common. You have this angle and this angle. Complementary. The way I've always remembered complementary is that the C can be turned into a 9. So that the first letters of the word complementary tell you that it's 90 degrees. 9, 0. Complementary are two angles that have a sum of 90 degrees. So I could have two separate angles, non-adjacent angles, that have a sum of 90 degrees. So let's just say this angle is 60 degrees and this angle is 30 degrees. Well, 60 plus 30 is 90. So these two angles are complementary. You also can have a scenario where you do have adjacent angles. Say right here. Well, clearly this is not an angle bisector because this angle has a larger opening than this angle. So these aren't angles that have been bisected. These are just complementary angles where we can tell that if we add this angle to this angle, it has a sum of 90 degrees as depicted by this box here. Then we have supplementary, and those are going to be two angles with a sum of 180. And I always remember that because you could take the S, draw a line down it, and it looks like an 8. And that prompts you to remember that supplementary is the one that's 180, not 90. So once again, you can have two non-adjacent angles that have a sum of 180. So let's say we had this angle and then an obtuse angle. And this angle is 30 and this is 150. Well, then these two angles, 150 plus 30 equals 180. So these two angles are supplementary. But you can have a scenario where the two adjacent angles are supplementary. So you've got this angle, go back to our 30 degree, and then let's extend it and make that 150 degrees here. So you have your 150 here and you have your 30 here. Well, that's going to be a linear pair. That's when you have adjacent angles, so they share a common ray. You have adjacent angles with a sum of 180 degrees. 150 plus 30 is 180. And the way that you can recognize it is that each angle has a ray going in the opposite direction. So the vertex. So here's the vertex, and this ray is going this way, this ray is going this way. So you have opposite rays forming a straight line, and then you've got a ray coming out of that vertex. That's your linear pair. And the last angle relationship we have is vertical angles. Vertical angles are formed by two straight lines. So let me get a straight line here. So here's my two straight lines. Now if these two straight lines come together at a vertex or a common point, that's that point right here, then the non-adjacent angles form vertical angles. So non-adjacent means that without a common ray, they can still exist. So there's this angle that can exist alone, and there's this angle that can exist alone. Those are your non-adjacent angles, and those are your vertical angles. So here, this angle is vertical to this angle, and this angle separately is vertical to this angle. And the thing you need to know about vertical angles is that they're congruent. So if this is, let's say, 87 degrees, then this angle across from it is also 87 degrees.